about ARM assembly today. The ARM assembly, it's a newer architecture, newer than x86 and MIPS, that's being more and more frequently used in a lot of devices that we work with today. A big part of that is mobile devices, and as we've seen recently, also some larger scale devices, including supercomputers, MacBooks for sure, all on ARM architecture. So we're going to talk about why that is and why ARM is becoming so much more prevalent. Um, so ARM is a newer type of architecture here. It's meant to lower the amount of power that is being used by the CPU. It's also meant to have a shorter and more compact instruction set. And so that's kind of what the part of the R stands for inside of it here. Um, and so going through different parts of it, reducing power consumption, energy, and efficiency inside the ARM architecture. The big thing is how it lowers the power requirements and extends battery life for mobile devices. So, for instance, my iPhone would be running on ARM architecture, and actually, this has been the case since 2005. Since 2005, ARM architecture has been used on the majority of mobile devices, and that's just because it's so energy efficient. And it actually, matter of fact, is slightly cheaper to make than other architectures for mobile devices. And so, since it's a bit cheaper to make and it's more energy efficient, it's definitely been the go-to and the one that's really stuck through on most mobile devices, and it's still holding true today. Um, where a majority of mobile devices are using some kind of ARM chips for their CPUs, at least for part or all of their CPU. And so, yeah, the energy efficient design contributes to reduce operational costs and makes everything easier on the phone. The Internet of Things devices with a limited power supply, ideal for Internet of Things. So that's just talking about like smart devices like mobile phones, smart watches, your smart refrigerator, even. And even things like smart security systems are all going to be using this architecture because they have limited power supplies, and it's still able to do all of the same kinds of things. Um, there are other advantages to ARM architecture here, so scalability and versatility for various devices. The ARM architecture supports a wide range of devices, from smartphones to supercomputers. It's enabled efficient design for any kinds of applications. It also has very scalable architecture and allows for easy customization and adaptation to specific requirements. And so we'll talk about that a little bit later here, especially when we're going through enhanced performance through instruction pipelining. So, yeah, this is a huge thing with ARM here too. So it has a lot of advanced pipelining techniques. The actual circuitry involves less transistors and a lot of things that make the whole CPU more efficient. It enables faster clock speeds, reduces latency. There's also support for multiple instruction sets. I thought this was really, really interesting when I was doing my research, that there's actually different instruction sets that you can run on ARM chips. There's a couple of reasons for this. So originally on the Thumb and Thumb 2 were the earlier ones. Those involved 16-bit and 32-bit instructions. Um, while the AR32 and 64 are on some of the more advanced chips. Those are what the more advanced chips that we use today are running on. But each of these would work on these devices, and they're all backwards compatible. And the nice thing about each of these is that they each have their place. And so the thumb architectures, the thumb instruction sets are really meant for energy efficiency. And so you'd see those on like a lot of like older smartphones and older devices when like power really wasn't something that was heavily available. And so those thumb instruction sets are made to lower the amount of memory that was being used, memory accesses and cache writes, as well as making sure that the instruction set was as compact as possible. And then the 32 and 64 instruction sets provide compatibility and performance benefits, but each of these allows for a lot of flexibility based on requirements because you can do different instruction sets based on what you need to do. There's also a lot of availability to developers for ARM processors. There's a larger and more developing ecosystem. It's not quite what other ones are, which we'll talk about, but it is getting bigger and more libraries in development. A lot more tools for people to innovate using ARM architecture here. So there are some drawbacks too to ARM architecture. There's limited support for complex calculations and floating point operations. That's something that x86 actually is going to beat it at. Floating point specifically, floating point capabilities, x86 just has more extensive ability there, and those architectures just offer a little bit more with the way that they're built and the circuitry is built. And so some scientific things are going to be more suited for x86 technologies, which is just the way it is currently. Um, there's also a dependency on external memory for larger data processing, and so ARM processors have limited on-chip cache and memory capacity compared to others, and of course, as we develop ARM processors more and more, this is becoming less and less of a weakness, and it's really not as important as it is now. Fewer options for advanced debugging and profiling tools. I thought this was really interesting, and it made a lot of sense to me. Since ARM architecture is such a new thing, there's not going to be as much out there in terms of libraries or tools for debugging as there would be for other older assemblies like MIPS and x86. And so there's a bit less to work with. And so new people working on ARM architectures, it definitely takes a bit more time. It's a bit harder to find issues. So since x86 is such a mature ecosystem, it's sometimes just an easier one to go off of. There's so many, even niche little categories that it can be used upon. While ARM's tools are continuing developing and improving, but there are limited options. And you can even see this with Apple's rollout of the M1 and M2 chips, because a lot of programs don't natively run an ARM assembly. And so Apple's had to develop a couple virtual machines to allow other programs written for something like x86 to run on their ARM assembly. Only a few programs have actually compiled themselves to run on ARM assembly, Adobe being one of them. And it's going to take a lot of time for programs to come around to doing this, because it's just not as easy as other architectures because of the environment. So to kind of go through it here, there's the last couple of things. I wanted to show a comparison of the instruction set of ARM to x86. I've worked with x86 before, so it's interesting kind of seeing like the differences. It has the R registers. It uses R0, R1 through all the way through R16. It has similar registers to x86 in terms of having like a register for a stack pointer, instruction pointer, a base pointer. So each of these is important here. You can kind of see some similar commands, adding commands, which it'll, instead of MIPS, it just has an add. You can add immediates or not. This is the load command over here, which is using in place of a move command in x86. So there's some really nice ones in there. Here's another breakdown of different commands possible in ARM architecture. And each of these, again, a lot of these are very similar. But there are some differences. The load command works a little bit differently, which allows, as you'll see a bit later, it allows for some more efficient running of certain things. So below this, we also have some C code to ARM assembly. I thought this was important to show, just to kind of see the comparison of what ARM is going to look like with an older C function. So we just took the sum function in C and showing this in R, using sum, a label similar to MIPS, push LR, adding 2 registers, saving them into R2, and then we would be moving whatever's in R2 to R0, excuse me, and then restoring the return address and returning everything from there. And so this would return the label sum, everything would work here, and this kind of goes through all of that as well. So another important comparison that I wanted to make, since x86 is so well known, is showing an actual problem being solved in x86 versus ARM. So the problem I decided to go through is summing an array. So up top here we have the x86 example. You can say sum array, goes through a lot here. It has a loop start, a loop end, and there's some jumping commands, jump loop start, jump if equal, loop end. So there's a lot of jumping around in the x86, and I wanted to highlight just the more compactness of the ARM assembly, and you can see that here. The code is definitely a lot more compact, and there's a couple reasons why this is the case. It uses the branch if equal construction instead of the jump if equal, which allows for more concise branching instructions going from place to place. It also takes advantage of load store architecture and uses the LDR instruction to not just load the current element directly from memory into a register, but also increments the array pointer in a single instruction. So some of these things are super, super useful in ARM, and this is why ARM is becoming more prevalent, because it's such a simple, it's a lot more simple, a lot more compact to write than x86 would be. So there it is. There's ARM architecture here. It's definitely a growing phenomenon, and it's going to be growing more and more and more because of what it offers. And I believe the drawbacks of it are definitely going to become less and less important as time goes on. Thank you.